The Earth has a diameter of 12,740 kilometers, yet humans have barely penetrated its surface. Most mining operations are limited to the upper 7 kilometers of the crust. Kola Well, a research well in northern Russia, is only 12.3 kilometers deep. How then have scientists learned about the composition of the Earth's interior? Knowledge of the Earth's inner makeup has been gained by the study of seismic waves, which are produced by earthquakes and controlled nuclear explosions. During such an event, seismic waves radiate out in all directions from a focus or point of origin. They pass down through the Earth and emerge at distant points, and also travel along the surface. The waves that emerge at distant points carry information about the materials that they've passed through, and are recorded and analysed at seismographic stations. Seismographs are instruments that are used to record seismic waves. Today, hundreds of seismographs measure seismic activity all over the world. There are two major types of seismic waves. Body waves travel through the Earth's interior, and surface waves travel along the ground's surface. In an earthquake, body waves are responsible for the sharp jolts, while surface waves are responsible for the rolling motions that do most of the damage in an earthquake. Seismic waves travel at different speeds and reflect or refract depending on the type and properties of materials they encounter. When a wave refracts, it changes direction slightly, and this behaviour is evident at the boundaries between two materials that differ physically or chemically. In general, seismic waves travel fastest through materials that are rigid yet elastic, that is, resilient solids. Temperature and pressure also affect seismic waves, with pressure having the greatest influence. Higher temperatures slow seismic waves, while higher pressures speed them up. By measuring the reflection, refraction, and travel time of seismic waves, scientists have been able to make discoveries about the Earth's interior. P waves, also known as primary waves. P waves are a type of seismic wave that compress and expand rock the same direction that the wave is travelling. If you were looking towards the earthquake epicenter as the P wave travelled underneath your feet, you'd be shaken forwards and backwards. P waves change the volume of the substances they pass through, temporarily compressing and expanding them. Because solids, liquids and gases resist change in volume, these materials spring back to their original volumes once the P wave has passed. The elastic quality means the P waves travel through solids, liquids and gases. Of the seismic waves, P waves travel the fastest. S waves, also called secondary or shear waves. S waves are a type of seismic wave that shake rock at right angles to the direction the wave is travelling. If you were looking towards the epicenter of an earthquake again, as the S wave travelled underneath your feet, you'd be shaken up and down. S waves temporarily change the shape of the materials that they pass through. This means that S waves are only transmitted through solids. Solids can elastically spring back their initial shape after an S wave has passed. Liquids and gases do not have this ability because they flow and lack fixed shapes. S waves travel at about half the speed of P waves. In 1909, Yugoslavian scientist Andrija Mohorovičić differentiated between Earth's crust and mantle. He noticed that seismograph stations located far from a shallow earthquake recorded P waves with faster speeds than those recorded at stations closer to the event. P waves that reach more distant stations travel at greater depths of the planet due to the Earth's curvature. This was evidence that a layer of material with different properties exists beyond about 50 kilometers below the Earth's surface, and that this layer was slowing down the P waves. This boundary separates the oceanic crust and continental crust from underlying mantle, and came to be known as the Mohorovičić discontinuity, or the MOHO for short. Benno Gutenberg discovered the core mantle boundary in 1914. He noted that P waves diminish and die out roughly between 105 and 140 degrees away from an earthquake. This area is known as the P wave shadow zone. Gutenberg said that the shadow zone could be explained by the existence of a central core within the Earth that is composed of materials that differ from the mantle. It was found that the core creates the shadow zone because it causes P waves to refract. Later research revealed that S waves do not travel through the core at all, and P waves slow down by about 40% in this region. Because P waves travel more quickly in solids than liquids, and S waves do not travel through liquids at all, scientists concluded that at least part of the core must be liquid. Further study throughout the mid-1900s revealed that seismic waves change direction and speed along a region within the core. Thus, the core came to be divided into two distinct regions. Because P waves that penetrated the inner core travel faster than those that penetrate through only the outer core, researchers concluded that the inner core is solid while the outer core is liquid.
Earthquakes generate two main types of seismic or shock waves: body waves and surface waves. Body waves travel through the interior of the Earth. The fastest of these are primary or P waves. These compressional waves move faster in dense rock and slower in fluids. Thus, their speed and direction change. Because they are deflected by the Earth's core, P waves are not seen in the so-called shadow zone. The slowest body waves are secondary, or S waves. S waves are elastic shear waves that move material sideways at right angles to their direction of travel. Because secondary waves travel only through solids, they do not penetrate the Earth's outer molten core. For this reason, there is also an S-wave shadow zone. The slower seismic surface waves do not penetrate the Earth's interior, but follow the surface. One type of surface wave, the love wave, travels in a circular motion and causes damage by displacing materials horizontally. Love waves can be very damaging. This cracked pavement and these twisted railroad tracks clearly demonstrate their destructive power. Earthquake damage also results from Rayleigh waves, surface waves which deform materials vertically.
Let's talk about different kinds of seismic waves and their paths that they travel from an earthquake to a distant seismic station. One kind of waves, the body waves, travel through the interior of the Earth. These are of two varieties. There's P waves, or sometimes referred to as pressure waves. They're the fastest. There's S waves, or shear waves, which are slower than the P waves, but they're faster than the surface waves which go around the perimeter of the Earth. The ray path, the path that these P waves and S waves will travel from an earthquake up here to a seismic station over here would be through the interior of the Earth, through Earth's mantle. And in general, the P and S wave velocities increase with depth into the mantle. So they're going faster and faster as they go deeper into the Earth, and then they slow down as they approach the station from below. In addition to these body waves, we have the surface waves, which travel around the perimeter of the Earth. They oscillate the outer few tens of kilometers of the Earth. There are two varieties of these, Rayleigh waves and love waves, named for the people who discovered them. So their path of travel would be around the perimeter of the Earth, shown by this set of arrows here, because they travel in the materials near the surface, which have lower seismic velocities, slower velocities. They will arrive substantially after the body waves have already arrived at a distant seismic station.
Continuing seismic research has allowed scientists to gain a greater understanding of the crust, mantle, and core, and distinguish additional layers within those areas of the Earth. The crust is the Earth's thin, cool, outermost skin. According to seismic research, the crust ranges in thickness from 3 kilometers at the ocean floors up to 70 kilometers in the continents. Thicker and less dense than the oceanic crust, continental crust is composed of rocks rich in silica, such as granite. Thinner and denser oceanic crust is composed of volcanic rocks, such as basalt. The mantle lies directly beneath the crust and extends to a depth of about 2,900 kilometers, where temperatures approach 3,000 degrees centigrade. It is made up of materials rich in iron, magnesium, and calcium. Because S and P waves travel through the mantle, Scientists know that it behaves like an elastic solid. The core is the innermost sphere with a radius of about 3,486 kilometers. Here the dense iron and nickel that make the core can exceed temperatures of 6,000 degrees C. The outer core is a liquid layer, while the inner core is under such immense pressure that the material behaves like a solid. The lithosphere is made up of the crust and the uppermost mantle. It is about 100 kilometers thick on average. Meaning sphere of rock, the lithosphere is a rigid shell that surrounds the Earth. It is broken into large pieces known as tectonic plates that we discussed earlier. The asthenosphere, which means weak rock, is part of the mantle and lies directly below the lithosphere. Temperatures are high enough and pressure is low enough in the upper part of the asthenosphere to allow some melting of the rock. As a result, the plates of the lithosphere can move about upon the asthenosphere. The mesosphere, or lower mantle, lies below the asthenosphere. Here the rocks are more rigid due to the increased pressure at this depth. The rocks are at a higher temperature as well, and are capable of very gradual flow.